Sir, dear participants, kindly switch off your videos and mute your mics. Choice 2020. Thank you, sir. I will be starting the session within 5 minutes. There is a little difficulty at the resource person side.
Dear participants, please wait. Our resource person will join within few minutes. Dear participants, a small technical problem. Our resource person will join within 2 minutes. Please wait. Dear participants, sorry for the inconvenience. Our resource person will join within 2 minutes. Please wait. A small technical problem, sir.
Sir,
Sir, good morning, sir. Sir, you can share your screen.
Mohan Rao, sir, first unmute your mic and then share your screen, sir. Mohan Rao, sir, please unmute your mic and then share your screen, sir. Yes, sir. Yes, sir. You are unmuted your mic.
Yeah.
Now share the screen, sir. Go to present now, sir. On the
Yeah, I'm
back.
doing.
Sorry, any help, sir?
No, it's not. It's not showing. That's what I'm wondering. Still says not responding.
Sir, otherwise, if you don't have any
Yeah.
objection, can you share that PPT to our coordinator, sir? PDF format also. We can share that PDF format. You can
Because
talk on the topic, sir.
now the PPT I shared, is it showing?
No, sir. Through mail, I'm asking, sir. Through mail, if you are sharing to our coordinators, we will share the PPT from our side, sir.
But then I can control the.
Yes, sir. No, just you can continue based on the slide. You can continue, sir. No problem, sir.
Okay, I'll do that one also, but I don't know why it is not sharing.
Sir, go to present now. I have gone to the present now, sir. Present now.
Yeah, I did that one.
You got any window, sir? Another window?
Yeah.
Pop-up window. Pop-up window.
Yeah, share an application window.
In that you choose a window option.
Yeah, it shows window.
Go to that OK. Or otherwise you click window double 2 times, sir.
See, it is not sharing. I don't know why. See, this one present view. Okay. Now I have to share this window. I could share.
The PowerPoint is not responding.
No, it is responding.
Now it's sharing.
Sharing.
Now it should be sharing. Ask them.
Rajesh, it's sharing now.
No, sir. No, sir. No, sir.
But it says sharing.
Rajesh, you guide.
No.
Rajesh?
Sir. Yes, sir.
No,
Yes, sir. I'm here, sir.
It's sharing.
But we cannot see, sir. That is the problem. Inkokkasari, you please repeat, ma.
Okay,
You stop sharing. You please
Oh.
repeat, sir.
I'll do it.
I'll just move the camera forward.
Window.
Ma, please go to present now. Then you click a window, and you please select the PPT.
Yeah, that's
Before
what I
selecting
did.
the PPT, the PPT must be opened at the background.
Yeah,
Is
it
it
was
so?
there.
Can you see it now?
We will wait. Just you wait because the net may be slow. No, we cannot see, ma.
Okay, just give me.
Save as PDF and send.
Hmm.
Window.
Can you see now?
Now is it sharing?
Yes, sir. Yes, sir.
Yes, sir.
Yeah.
Sir, Ma, you please press F5, Ma.
No.
Sir,
Yeah.
presentation mode. Go to F5, sir.
Yeah.
Presentation.
Yeah. Is it okay?
Yes, sir.
Yes, sir. It
sir.
is
Okay.
crystal clear, sir.
Sir,
Yeah,
shall
okay,
we
fine.
start, sir?
Fine.
Shall we start?
Yeah. Already delayed.
Thank you, sir. Thank you, sir. Good morning to one and all present here. I welcome all the participants to this phase 4 6 days short-term training program on nanotechnology and functional materials. Now we are going to start fifth day and first session. Once again, thank you for joining with us. Now let me introduce our resource person, Dr. G. Mogan Rao, Professor Emeritus, Department of Instrumentation, Applied Physics from Indian Institute of Science, Bangalore. He has completed doctoral degree on thin films from Indian Institute of Science, Bangalore. He has guided more than 25 research scholars and 13 PG scholars. He had published more than 325 research articles and in reputed international journals and conferences. He has citations more than 4,500 and his cumulative impact factor is more than 500. He has obtained 5 patents for the benefit of society. He has completed 9 research projects and 5 consultancy projects and having book chapter also. He has developed many technology and transferred to industry. For example, high pressure oxygen sputtering of high tech oxide films provided to Vacuum Techniques Bangalore, large scale magnetron sputter cathodes for industrial application provided to Hindustan High Vacuum Cooperative Limited, Bangalore, plasma surface modification of PMMA for intraocular lens application provided to Aurolab Madurai, and also patented. We welcome you, sir. We are honored with your presence, sir. The current session topic is thin film microbatteries, power sources for next generation devices and material issues. Now, I request our resource person to proceed with the session, sir. Requesting, sir.
Okay. So, good morning, all of you. I'm very sorry for the delay in clearing these technical glitches. Nevertheless, we'll proceed with the topic. This on thin film batteries is something different from the batteries that you come across every day. Now, these batteries have become part of our life, and I'm sure all of you who are participating in this lecture are having a battery with you. That battery is in your mobile phone, because there is nobody without a mobile phone these days. Now, in our childhood, we have seen batteries which are different from the battery that you have got in your mobile phone. And what we are going to talk today is about a battery which is for the next generation. Now, these batteries. Now, if you Google for batteries, in all probability, you will come out with this slide, which shows a clay jar with an iron rod in the center and filled with vinegar and an electrolytic solution. Though it says it dates back to 250 BC, I really do not believe this. Okay, but let's not worry. This is only for a historical perspective. But then the scientific work on batteries could be established to the year 1600, where the first electrochemical study has been reported. Now, you all are aware that a battery is an energy storage device which is based on electrochemistry. It has got a cathode, anode, and an electrolyte. Due to the migration of ions and electrons to their respective electrodes, you get a EMF. Now, the electrochemical study, which started in the year 1600, progressed gradually like any other scientific study. And the first voltaic cell was developed in the year 1800 by Volta in Italy. Then, within a couple of years, this battery has been produced in large scale, that is a mass production. Then there were developments on different kinds of batteries, which we all studied in our high school days, which are Daniel cell, Leclanche cell, and dry cell, etc. Now, the most advanced scientific achievement has been done in the year 1899 with the invention of nickel-cadmium battery, which is a rechargeable battery. Then nickel-iron battery came. Then a lot of other alkaline batteries have come. And finally, the most important development of the previous century was the development of lithium-ion battery, which is what we see in our mobile phones these days. So the battery technology over a period of 400 years has seen a lot of revolutions. Now, if you compare your batteries that you come across, on the top left, you see the lead acid battery that you use in your automobiles. Then next to that, you see the ASL, which you use for your torchlight. On a smaller size, you use for your other devices. Then came the most important this thing, that is the button cell, which is a miniaturized version of your tri-cell. And these are all not rechargeable. They are use and throw. Then comes the lithium-ion battery, which every day religiously you recharge so that your mobile is always working. Now, what we talk today will be the next batteries that you see here, which look like your microelectronic chip. And then at the extreme end is what is envisaged, a flexible battery, where a battery is printed onto a flexible polymer sheet so that you can roll it, fold it, pack it in a box and take it with you wherever you want. And even when there is no sun or anything, you can use this battery to power your devices. Now, the batteries that we see come in different kinds of sizes. A small form of batteries, which we are talking today, they weigh less than a gram in weight, and they have a capacity of 10 microampere hours to 1 milliamp hour, and they could be used for disposable and autonomous systems like wireless sensor networks, pacemakers, and other things, or your microelectronic devices. Then comes a next generation, which is 10 milliamp hours to 1 ampere hour, which are slightly heavier, maybe up to 100 grams, which could be used for your laptops, tabs, and all that. Then, for automotive transportation, you have 10 ampere hours to about 100 ampere hours. And for large power backup, you have 10 kilowatt hours to megawatt hours also. Now, the technology for all these batteries will be totally different. And let us concentrate only on this small form of batteries, which are thin film batteries. Now, the application areas, as I said, the small batteries, which are about 5 millimeter by 5 millimeter size, which are less than 50 microampere hour capacity, could be used as a backup for a real-time clocks or memory backup. Now, slightly bigger ones, 25 by 25 millimeter, which could give you 1 to 10 milliamp hours, could be used for RFID tags, smart cards, smart keys, and wireless sensor networks, and all this. And large area, which can give you a capacity of more than 10 milliamp hours, could be used for consumer electronics, telecom, and medical devices like pacemakers. Now, the batteries that you come across in your life could be classified into primary batteries and secondary batteries. Primary batteries are your alkaline batteries, zinc air, which could be used for consumer electronics, hearing aids, and all that. They are of the cylindrical cells, button cells, and they are not rechargeable. That means you charge once, you use it, it gets discharged, and then you throw it. The next battery, which are secondary batteries, which are rechargeable batteries, the examples are nickel metal hydrides, nickel cadmium, lithium ion batteries, lithium polymer batteries, and lead acid batteries. And then the next generation is what is solid state thin film battery, which are primarily, as on today, based on lithium ion batteries technology, which uses solid state electrolyte, which could be used for microelectronic devices. It could be of any shape, and it has got long cycle life and long shelf life. What is this shelf life? Most of the times you would have seen that you purchase a battery today, somehow you don't use it. Whether you use it or not, over a period of few months, it gets totally discharged. So when you have a work with that battery, you switch on, it will not work. That means its shelf life is very small. So the batteries that we are going to talk are based on solid state electrolyte technology, which means that there is no leakages. So the shelf life is very high, and it could be recycled for 2,000s of times. Now, if you look at this chart, it gives you an idea of what the importance of this lithium-ion battery technology. On the x-axis, you see volumetric energy density, and on the y-axis, you see gravimetric energy density, which means that for a given capacity, what will be your battery size and what will be its mass. Lead acid battery, as we all know, has got very low volumetric energy density and very low gravimetric energy density, which means that if you are trying to draw more power, the battery size will be huge and it will be heavy. Now, compared to that, nickel cadmium cells are slightly better. Nickel metal hydrides are still better. They are lighter. And these lithium ion batteries can have more volumetric energy density and more gravimetric energy density, which means that in a small size and a low mass, you can have very high capacity. Now today, lithium ion batteries have got more than 75% market share for many portable applications. Now, the advantages of lithium ion batteries, which are commercially available since early 90s, they have got high specific capacity, twice that of nickel metal hydride, and about 6 times that of standard lead acid battery. They lose only about 5% of charge per month compared to 20% of nickel metal hydride. And most important aspect of this lithium ion batteries is that, as you all aware, all the batteries that we use give you 1.2 to 1.5 volts output. But these lithium ion batteries are high voltage batteries, which give you 3.8 volts, which is almost 3 times that of the normal battery cell. So that is an advantage. Now, how does this lithium ion battery work? Before we get into this, let me tell you why people started looking at making a battery in a thin film form. I'm sure most of you are aware of what these thin films are. Now, thin film is nothing but, it's again a material in a microscopic form. It has got dimensions which are macroscopic across the length and width, but along the thickness, it is a microscopic. It will be less than a micron thickness. Now, why do we need this? For most of the applications, we do not require the bulk material, but it is a surface phenomena that we use for applications. For example, if you are trying to draw a current of less than a milliamp, what is the point in using a wire which is 1 mm thickness, which can draw current of 5 amperes? So, when the microelectronic revolution took place, when the power consumption for the devices has come down, people started making microelectronic devices with thin film electronic components like resistors, capacitors, and all that. And the interconnects also were made by thin films. So the thin film technology grew along with the microelectronic technology. So then people thought in early 80s, when the integrated circuits have entered the phase of VLSI, though the size of the chip has come down to less than 1 centimeter by 1 centimeter, with a density of a more than million transistors, but the way you power this device is still the old. You need a regulated power supply to power this device, or you use a big battery. So then people thought that if I am able to develop this microelectronic device on such a small scale, using the same process technologies, is it not possible to build a battery also into the device so that the entire device or the so-called chip can become self-sufficient? So it has got a power source, it has got the circuit, everything, and you keep using it without any external power source. So with that idea, the research on thin film batteries took off in early 80s. Now, after 40 years of research, at the end we will see where we are. Now, the first hurdle when you want to make a thin film battery is that, as I said earlier, a battery has got a cathode and the anode, which are electrode materials, metals. But the important aspect is the electrolyte, which was a liquid. Now, if I am trying to develop a thin film battery, I cannot use a liquid electrolyte. So at the time, the polymer gels have replaced liquids as an electrolyte. Still, that cannot be used for microelectronic devices. So the first task was to develop a solid state electrolyte material, about which I'll tell a little later. Now, before we understand this thin film batteries, let us understand how this lithium ion battery you have in your mobile phone works. So it has got a current carrying collector onto which there is a cathode, which is typically a lithium based compound, lithium cobalt oxide, LiCoO2. That means one lithium ion atom, one cobalt atom, and two oxygen atoms is the cathode material. And then comes a solid state electrolyte, which is going to be what is called LiPon, Li3PO4, lithium phosphate, in which some oxygen is replaced by nitrogen so that it becomes more ionic conductor. Whereas in your mobile phone, you do not have the solid state electrolyte. What you have got is a polymer gel material which replaces the slip-on. Then comes the anode, which could be a electrochemically active metal. And in our case, we are going to see how tin could be used and why tin has to be used. Now, this is the assembled battery that you have in the totally discharged state when you assemble it. Now you start charging the battery. When you start charging the battery, the lithium from the cathode migrates towards the anode through the electrolyte, and this process is what is called intercalation. Now you keep charging it. Based on this reaction that is shown here, electrons are generated. Once it is in a fully charged state, you see that a virtual layer of lithium has formed between the electrolyte and the anode. So now it is in a fully charged state. Now on the cathode side, you see that almost 50% of the lithium has come on this side. For the structural stability, it loses only 50%. If you try to draw more than 50% of lithium, the cathode loses structural stability and it collapses. Now, once you are in a charged state, now you try to use it. That means you are trying to discharge the battery. Now, when you start discharging the battery, the lithium that has gone on that side will come back to its original position. And by the time it is fully discharged, all the lithium should come back, ideally. But it doesn't happen. Sometimes some lithium is left behind because it feels more comfortable here. It doesn't come back. Now, because of this, what happens? For the next cycle, when you are charging, the capacity will reduce. So with each cycle, if some lithium goes and sits there, finally the battery will die. Now, when you try to make a good battery, the first important aspect is that all the lithium that has gone here should migrate fully, and whatever has gone should come back. That means ideally this should be a porous structure for the anode. The second aspect is that when the lithium goes from the cathode to the anode during the charged state, there is a volume expansion that is taking place. And when deintercalation takes place, that means when it is getting discharged or when the lithium is coming back, there is a contraction that is taking place. That means during charge-discharge cycle, your battery is undergoing volume expansion and contraction. So the structural stability is very important to accommodate this volume expansion and contraction. Is number two. Now, when you are trying to make a thin film battery, if you are making a bulk battery, then there is no problem. you have all the powders, you put everything, so it is a porous structure. You do not have this volume expansion and contraction problems. But when you make a thin film, that means you take a substrate onto which you deposit a thin layer of lithium cobalt oxide, then another layer of lipon, and another layer of the anode material. So there is no place for any volume expansion or any new fellow to come. Now, in such case, what happens when there is a volume expansion takes place? At the interface, there will be a lot of stress. So the film will peel off. So the battery will collapse. So one has to be really careful with the process to make your layers deposited such that this volume expansion and contraction business is taken care. Let us see how one can do that. So, having known something about this battery, let us see what a thin film battery looks like. Now, a thin film battery is a robust, rechargeable, micro-sized solid-state energy storage device. That's how you can define. It has got extremely long cycle life, very low self-discharge, high power capability, etc., etc. And it is very safe because there is no liquid electrolyte. Now, what is this liquid electrolyte problem? Why it is not safe? When Sony developed the first lithium-ion battery and they used it in their mobile phones, there were heavy casualties in the sense that during charging, the battery blew up, causing casualty of the person who is standing nearby. Now, what happens is that in bulk batteries, over a period of time, the anode used was carbon, graphite. And this graphite forms dendrite structures, and through the electrolyte, it pierces through and touches the cathode material during charging, and it short circuits, and that's how sometimes the batteries blow off. Even today, not that often, but still we come across news items which says that the battery has blown up while charging. So this is the reason. Whereas in thin film, there is no liquid electrolyte, so the dendrite formation doesn't take place. Now, as you look at this structure of a thin film battery, it has got a substrate. That means a substrate has to hold the thin film that you are going to deposit, because the total thickness of the battery that we are talking is of the order of about less than 10 micrometer thickness. So for a structural stability, it should be placed on a substrate. Now this substrate doesn't play any role in your battery, so it could be anything. If you remember in the first slides, I have shown that tomorrow you can have a battery or a polymer sheet also. Okay. So this is what it is. You have got a substrate which originally thought to be silicon because they wanted to make it for microelectronic devices. Then you deposit a current electrode, current collector, and then you have a cathode layer, that is lithium cobalt oxide. Then an electrolyte layer is built onto this one, that is your lipon, and then there is an anode layer, and then a current collector. As I said, the entire thickness of this battery is less than 10 micrometers, whereas your silicon substrate is not less than 250 micron thickness. Now it could be fabricated on any shape, size, etc., etc. You could use any substrate, silicon, alumina, quartz, polyester, kapton, whatnot. Anything could be used. Now, as I said, the issues when you make thin films of any material is that, if you remember, we said lithium cobalt oxide is electrochemically active when it is LiCoO2. That means when you are trying to deposit a thin film of this material, the thin film also should have these elements in the same proportion: 1 lithium, 1 cobalt, and 2 oxygen. That's first issue. The second issue is that you are having a substrate onto which you are depositing cathode layer, and then electrolyte layer, and then anode layer. That means each of these layers should stick together effectively. Then the third important issue is It should be able to take care of the volume expansion during lithiation and contraction during delithiation process. And finally, it should be stable against ambient conditions. What is there in the ambient? Most of it is water vapor and oxygen, nitrogen. Nitrogen in a case doesn't react with this, but water vapor and oxygen, it reacts. So the entire device has to be packed properly so that it is protected from the environment. Now, having understood the issues involved in making a thin film battery, let us see how one can realize these thin film batteries in real life. Now, these materials are well studied in bulk form, but then they have to be deposited in thin film form. So people use techniques like sputtering or evaporation to deposit any material in thin film form. Since this is a workshop on material science, let me tell you one important thing, that every day a lot of new materials are being discovered for several novel applications. But then it has come to a stage that no matter what material you discover, unless that material could be deposited in thin film form with similar properties, that material has no value, because today all the applications of this material have thin film form in it. That means miniaturization is the theme of any device today. And how you deposit these thin films is basically by these two important techniques. Though there are several other techniques, these two are still predominant techniques. One is evaporation, the other one is sputtering. Now, for the sake of people who do not know what this evaporation and what this sputtering, I'll spend a couple of minutes. Now, any material will have three states of matter. One is solid, the other one is liquid, the other one is vapor. So you have a solid material, and when you heat it, it becomes liquid, and you heat it further, it evaporates. Now, what is evaporation? Evaporation is the process at which the material will have a saturated vapor pressure, which is less, rather, which is equal or more than that of the surrounding pressure. Now, for example, if you take water, at normal room temperature, normal atmospheric conditions, we all know that at 100 degrees Celsius, water evaporates. It becomes steam, because at 100 degrees, its vapor pressure becomes 760 torr, which is equal to the atmospheric pressure. So it evaporates. Whereas when you go to Mount Everest, where the surrounding pressure is less, water evaporates at lesser temperature. You go to space, where the pressure is 10 to the power of minus 15 torr, which is 15 orders less than that of atmospheric pressure, you cannot hold water in a glass. It immediately evaporates. That means its vapor pressure is less than 10 to the power of more than minus 15 torr. So the basic idea here is that when you want to form a thin film of any material, you heat it in a vacuum environment. So when you heat it, its vapor pressure keeps increasing. So when the vapor pressure is more than the surrounding pressure, which is 10 to the power of minus 5 torr, then the material will start evaporating, and then it forms, it goes and hits a solid surface wherever it sees and condenses onto that and forms a thin film. So it all depends on how effectively you can heat it to the required vapor pressure. This is the typical evaporation process. Now, if you have got a single element in your material, then there is no issue. But then if you have got 2 or 3 different elements, then what happens? Each element has got its own vapor pressure. So all of them will not evaporate in the same proportion that is available in the bulk material. So this kind of technique cannot be used when there are multi-elemental materials. So people go in for another technique which is called sputtering technique, where you got this material, the material lattice, and then you bombard it with the energetic particle. Typically, you use ion. So when the ion bombards, what happens? It is like a carom board. In a carom board, what you have in the center, you arrange all the coins, whites and blacks. In the center, you will have a red, and then you have a striker with which you push towards the center. Depending on the angle at which you are hitting, and depending on the energy with which you are hitting, the probability of pocketing the white in the first attempt varies. Sometimes the striker may not even reach the lattice. Exactly similarly here, depending on the ion energy and the angle at which it is bombarding, the atom that is coming out from here will vary. So the ion transfers its energy and momentum to the surface atoms, and these surface atoms come out and travel because it is done in vacuum, and then deposit onto the solid surface that is kept in the line of sight. This is sputtering process. Now here is basically the energy transfer that is taking place. No heating is taking place. So no vapor pressure concept. So with this, if you try to develop thin film batteries in your laboratory, like any other materials research, you have to undergo all these steps. You start with the preparation of your substrate. That means you clean your substrate properly, and then you have a deposition chamber where you deposit a current collector, then another deposition chamber where you have the cathode layer deposition, then electrolyte deposition, then anode deposition, and finally the packaging and electrochemical testing. So these are all several steps that are involved in developing a thin film battery. This is on fabrication side. But then at the development stage, at each stage of this material development in thin film form, it has to be characterized so that you are sure that it has got same stoichiometry and same properties of the bulk materials. So you have to do all this kind of characterization for arriving at a final thin film battery, a device. So this talk essentially is on taking a raw material, how you end up making a device. So what are all the steps that are involved at each stage? We'll see what are the tools that we use. So these are all typical characterization techniques that you use, like FTIR, X-ray diffraction, scanning electron microscopy, and for chemical composition you have EDAX. And for a lot of cleaning and other things, you use organic solvents and metal salts, and then you synthesize a sputtering target. Then you do all this kind of structural characterization, electrochemical characterization, and multi-layer fabrication, and all this. So this is a typical sputtering system which is having 4 cathodes. So cathodes are having the material that you have to deposit in thin film form, and on the anode you keep your substrate or the wafer, which could be rotatable so that it moves from one target to the other target. So you start with metallization first, then cathode layer, then the electrolyte layer, then the anode layer, and then come back to metallization. So, and the gases that you are using are argon for striking the plasma, nitrogen for depositing lipon, because if you take lithium phosphate target Li3PO4 and put it in nitrogen plasma so that some nitrogen replaces oxygen. And oxygen is also introduced during deposition of lithium cobalt oxide, because when they are sputtering lithium cobalt oxide, there is a possibility of dissociation of some oxygen, so that has to be replenished by this external oxygen. Now, On the surface of your target, there will be a lot of contamination because it was exposed to the ambient. So initially that layers have to be removed, and at the development stage in a laboratory, one can use what is called an optical emission spectrometer to see whether your target is in good condition or not. How it works is that your sputtering process involves a plasma. Plasma is nothing but it has got ions and excited species of the materials that are present inside the environment. So as the material is getting sputtered, it gets ionized or gets excited, and then you collect the light through an optical fiber and give it to a monochromator, and this is what the spectrum that you see. Now, if you are sputtering lithium cobalt oxide in an argon and oxygen environment, the ideal condition is that you see lithium, cobalt, oxygen, and argon ions or excited species. If you see anything else, that is a contamination. So, in your spectrum, if you see those any other elements, you keep continuing the sputtering process by keeping a shutter on your substrate till you remove all the contamination. So only when you see the elements that are required, then you open the shutter and start the process. This is what is called target conditioning. And then comes a most important thing. At what pressure you have to do sputtering, and what should be the distance between your target and the substrate, and what should be the substrate temperature to get a stoichiometric film. Now, please remember, this is for the young people who are listening to this talk. Most of us do research based on what is called literature survey. When you start research, your guide will say, first go and do literature survey on this material, how people have formed this thin film. You come with some data. So somebody has put at this pressure, this temperature. So I'll also do this. Now, we also did like that. The student did exactly with the same conditions that are listed in the literature, but it did not work. Then we realized why we did not get thin film. Now, you have to remember one important thing, that the scientific literature has got certain issues, in the sense that if it is a technologically important research, people will not reveal the actual process parameters. Why should somebody take my hard work? That is the basic idea. So one has to use some common sense also. Now, what is the common sense when you are doing multi-elemental deposition using sputtering process? Let's take our own example of lithium cobalt oxide. Lithium, cobalt, and oxygen. Lithium is the lightest metal. Cobalt is heavy metal. Oxygen, okay, leave it. That's now gaseous form. You can put some oxygen into your system for any loss. Now you have got one thin fellow and one heavy fellow. Both started running from the target. Both will come out. But then what happens? The fat fellow will lose all energy fast. So halfway he loses energy. He will not be able to move further. So it means that if you keep your substrate away from the target, far away, then what you get will be only lithium, but no cobalt in that. So if you have to get both lithium and cobalt into your film, the target to substrate distance has to be optimized. So in the literature, it was mentioned as 10 centimeters. And if you put 10 centimeters, nothing will come. And the optimum distance is 4.5 centimeters. So similarly, you simulate what happens when you change the pressure. You come out with some pressure data where you see all the elements present in your film. So you use this target to substrate distance and this pressure and deposit thin films, and then you find out what is the cobalt and lithium atomic ratio, and then you optimize the process parameters. So here you see the simulated data and the experimental data. That means that this is where one has to deposit thin films. So with this, you deposit a thin film of lithium cobalt oxide. Now your job is not to just deposit a lithium cobalt oxide film, it should be electrochemically active because that is going to be the cathode material. So you perform an electrochemical study, or which is also called CV study. And then one is oxidation peak, one is the reduction peak. That means it is electrochemically active. So the film gave a charging capacity of 160 microampere hour per centimeter square and a discharge capacity of about 130 microampere hour per centimeter square area for 1 micron thick lithium cobalt oxide film. That means your lithium cobalt oxide is working. So now your job is whether it is rechargeable. Okay, now you keep working for several cycles and it worked for more than 30 cycles. So now it is rechargeable. So the first part of your battery is ready. Now you move to the electrolyte material. So as I said, liquid electrolytes have got very high ionic conductivity of the order of 10 to the power of -1 Siemens per centimeter. But your solid state electrolyte have got 10 to the power of -4 to -8 Siemens per centimeter. That is the ionic conductivity, which is very low. So the material that has been found to be capable of giving a ionic conductivity of 10 to the power of -6 Siemens per centimeter is what is called a lipon, which is nothing but Li3PO4 in which nitrogen is put. So this was patented by John Bates of Oak Ridge National Laboratory in USA, and till today, that is the electrolyte material all over the world people are using to make a good battery. Though there are several other new materials that have come out in the laboratory scale, but when you go to an application, still this is the material that is being used. So how you sputter this one is that you take lithium phosphate target Li3PO4 in nitrogen plasma, you sputter. So you sputter at a power density of so and all these conditions, and then you deposit a thin film of lithium phosphate, lipon, and then you measure, see whether nitrogen has gone into, because unless nitrogen goes in the required quantity, it is not ionic conductor. So you do an XPS and find out that nitrogen is there, and then you test its electrochemistry or electrochemical impedance to measure the ionic conductivity. By optimizing the parameters, you get this 1 × 10⁻⁶ Siemens per centimeter, which is close to that of its bulk value. Now, having achieved this, you are very happy. You go back, and next day you come back, and then again you check its conductivity. And within 24 hours, what you see is an amazing phenomena that its ionic conductivity reduced drastically. It goes to about 2 × 10⁻⁹ -9 Siemens per centimeter, which means that it will not work. Now you look at the surface of this lipon film, you see a lot of blisters that are coming, and you put it under microscope, then you see that this kind of eruptions that have taken place. Now, one of the reasons for cause this kind of eruption in thin films is what is called stress in thin films. This is what we always do. When there is an eruption, then we say that there is a stress in the film. Now, the stress comes because of the thermal expansion coefficient mismatch, lattice mismatch, and all that. So, ideally, we thought that this may be the reason. Then what we have done is that we deposited this lipon film on silicon, but with an intermittent layer of titanium. Now, when you are in a depressed mood, when you are stressed, ideally what you are supposed to do, you go and talk to somebody who can console you or who can take your stress away? Some wise man. Similarly, here that wise man is your titanium. Why titanium takes away stress from many of these materials. So you deposit the same lipon on titanium, but still the effect is same. On the left side without titanium, and this is with titanium. Still you see these eruptions. That means it's not stress, but something else that is happening. So you do all kinds of studies, and then it was found out that the lipon is reacting with the moisture in the environment and forming a gas called phosphine, pH 3, because of the phosphor that is present in your lipon. And this gas is trying to come out, and that's how these eruptions take place. So the lesson learned from this experiment is that once you deposit your lipon film, don't expose it to ambient conditions, but you store it in a dry environment or a vacuum environment. Then it will work. So now your second layer is also ready with the lesson learned. Now you go to your third layer. That is anode layer. So now what we want here is that now it is the anode which is taking this volume expansion contraction business. So it should be a soft material and it should be a porous material. So soft materials are tin, aluminum, copper, lead, etc. But lead is heavy. So we arrived at tin layer, that is SN. So you deposit SN because that is a low evaporation temperature. You deposit by evaporation process, and this is how you get the film. Then you do electrochemical study. It is working for several cycles. You are very happy. But then what happens is that for repeated cycles, the capacity drops. That means it is not porous. All the lithium that has gone on the other side has not come back. So the capacity reduction is more than 90%, which you do not want. So go back to your sputtering process, sputter tin target, do it at a very higher pressure sputtering. Then what you end up will be a porous structure like this. So again you check it for charge discharge cycles. Now this time, even after about 30-40 cycles, the capacity drop is less than 30%. That means it is working. Now what happens? You have all the three layers that have been separately optimized. Now the task is to put all of them together and see that it is working. Now comes the most difficult job. In a class, you got a group of intelligent people, so-called intelligent people, who always get first to few ranks. There is a competition among them. Now you want to get a project done, then you put these three intelligent fellows in one group, expect the project to be succeed. Then what happens? Most of the times it will not work, because each of these fellow tries to take the project in its own direction. He says, I am the boss, you have to listen to me. Now here you have got three different kind of films: lithium cobalt oxide, lipon, and tin. Each of them have got its own characteristics. They don't go along well. So you have to match the conditions properly such that they stay together in a cohesive way. Then only the battery will work as a device. Okay. So you deposit this, and for isolating each of this, you have different masks so that the battery structure is deposited. So you take a platinum coated silicon wafer and then do lithium cobalt oxide by sputtering. This is the cross section. This is a very dense structure. And then do lipon by sputtering. So you can see the cross section here. And then tin, a porous layer, by sputtering. And now this is the cross section of your entire battery. Cathode layer of 1.8 micrometer thick, electrolyte layer of 0.5 micrometer thick, and anode layer of 0.5 micrometer thick. So now your battery is ready. Now we have learned a lesson earlier that it should not be exposed to the ambient. It has to be packaged in the proper way. How do you package in a laboratory? You are developing in a laboratory. You are not an industry where the packaging technology is available. So, what kind of packaging that you use? Now use your common sense. All of us know Horlicks. You see a lot of advertisements for Horlicks. Horlicks is a good health drink, right from newborn to old people. But then, in a kitchen, when you go to mix Horlicks, there is always a precaution that you are not supposed to put a wet spoon into Horlicks. What happens if you put a wet spoon into Horlicks? Or even if the Horlicks bottle is not closed properly. The next day when you open the bottle, you don't see powder Horlicks, but you see solid rock-like Horlicks rock, which you cannot dissolve. It has to be thrown. Now what happened is that your Horlicks has reacted with the atmospheric moisture. Even one drop of water is enough to kill 1 kg of Horlicks. So it doesn't work. Now you go to a supermarket, you get Horlicks refills, polymer packaging. So we thought that is the best pack for making packaging for our battery. So we wrote to this Garware polyester, which supplies to the Horlicks people. So they generously gave us few sheets for research work, and they gave specifications of this packaging material. Its water vapor transmission rate is about 10 to the power of minus 3 grams per 100 inch square for 24 hours at a temperature of 100 degrees Fahrenheit and 90% relative humidity. And similar is the case with oxygen transmission. And it could be sealed at a temperature of 160 degrees in 2 seconds time. Now, and this polymer packaging is not a simple polymer. It is a multi-layer polymer packaging. It has got about 14 layers of metal polymer alternate layers to prevent this water vapor entering into your pouch and reacting with the Horlicks. So what you do is that you cut this into the required size, make a pouch-like thing. You take an iron box which you use for your clothes, you press it, it seals at the edges, then put your battery that you have deposited inside, take the 2 leads out, and then press it again. It seals here also. So you have a battery that is ready here. Now once your battery is ready, you have to test it. Unless it works, you are not happy. So it works. But then what happens? After about 7 cycles, the capacity drops, and in another about 2 cycles, no more charging, discharging, it is dead. So the packaging that you have done is not a fully foolproof packaging. Okay. Now you try to analyze what is wrong with your battery, where it went wrong. So you cut open, then you see that your layers are no longer layers. You see a lot of blisters like this, which we have come across earlier. Now you try to analyze each of these layers separately now. That means again you start your research back to square one. Go to each layer, do this cycling business, and then after a few cycles, you analyze. Now, in the lithium cobalt oxide, after a few cycles, what we have seen is that there are a lot of cracks like this that have been formed. So now you try to analyze why these cracks have come. Now, this is due to the stress in the cathode layer. Now, the curvature of uncoated substrate is the black one that you see. And after coating, because of the stress, the curvature has increased. So this much of stress is there in your tensile stress is there in your deposited film. Now you try to analyze what could be the reason for the stress. The expansion coefficient alpha of silicon, that is your substrate, is about 2.8 into 10 to the power of minus 6 per Kelvin. Whereas that of platinum is 9 into 10 raised minus 6. Whereas that of lithium cobalt oxide is 34 into 10 to the power minus 6. So where is 2.8, where is 34? Nowhere it's matching. So what happens when you are annealing your film to get the crystallinity, because of the mismatch in this thermal expansion coefficient, it is delaminating. So this is not the ideal solution. Now you test your lithium cobalt oxide with liquid electrolyte. Now what is done here is that we found out that if you are using aluminum, which has got thermal expansion coefficient, which is in between that of your platinum and lithium cobalt oxide. That means it acts as a buffer agent. So we deposited a layer of aluminum across this and then deposited lithium cobalt oxide. But the problem is that when you deposit aluminum, then you cannot heat it to very high temperature, not more than 450 degrees. So your capacity will little come down. So with that aluminum, you deposit this and then you optimize the parameters, and you have, even after 100 cycles, the discharge capacity has not fallen, and so it is a very good modification to the process that we have done. Now, then you have to protect the interface from moisture and oxygen. How do you protect the layers? What is done here is that after all the depositions are done, on the top we have done a aluminum oxide barrier layer to protect the entire battery structure from the ambient air. So this aluminum oxide has to be perfectly dense without any pinholes. And then you give a metal layer on the top and then take the connecting out. Now, to check whether this is really working or not, if you do not deposit this Al2O3 layer, then what you see here is a black one, which means that the top layer, metal layer, that is a lithium or aluminum, whatever you are giving, is getting oxidized. Whereas if you protect it with Al2O3, no oxidation is taking place. It is safe. That means a protective layer is a must. Now comes the most important thing. At the end of the day, you have to take the leads out. That means you have to connect two wires to this anode and the cathode layers. So what is done here is that you have made a tool to put a solder material at a controlled temperature, and this soldering is done in a glow box environment like this, and then it works. Now, each of these layers, as we said, have to be protected from the ambient. Otherwise, your recon is going to fail. So what is done here is that instead of doing in a normal sputtering system, a new kind of sputtering system has been designed, which could be placed in a glow box, so that start to finish, that means you put your substrate inside till you package the battery. After all the depositions, packaging everything, then only the battery could be taken out of the glow box. That means in between it has not seen moisture. So the device is going to work properly. So with this kind of equipment design, it started working again. So we optimized the parameters inside this glow box for each of these layers again, and then it started working. Now, this is the performance. Now, I showed two performance curves here. One is what we have done using aluminum deposition and then lithium cobalt oxide. The other one, the blue one, represents a commercial battery which is manufactured by Sinbet. Now, I tell you some story. This is useful for the faculty who apply for projects. We go to a committee, present your project, face a lot of questions from the committee, And then most of the times we will not be able to answer those questions because of irrelevance, in my view. And then you will not get the money because they are the deciding authority. So what happened is that when we proposed this project, we gave a value of about 50 microampere hour as the capacity for the battery that we are going to develop. Then one of the committee members asked a question that I saw in the internet that there are people who are manufacturing these thin film batteries which can give you few milliamp hours capacity, which is far higher than what you are proposing. So why should your project be funded? Good question. So in the internet, anything could be put. So people who follow the internet data, be aware of certain things. Whatever you see, whatever is given by Google Baba is not always correct. I can upload any damn thing into the internet, whether it is true or false. Lot of fake messages are there. So even if I don't have a company, even if I don't manufacture a thin film battery, I can still put that I am manufacturing a thin film battery with milliamp hour capacity. So this is what is seen. The second important thing, the definition of thin film battery itself is a different thing. An ideal thin film battery is one which uses process technology that is used in microelectronic industry. It means that it is an all solid state technology. But most of the so-called thin film batteries that you come across in the internet are based on polymer gel technology, which could be pressed and sandwiched and pouched, and it could be sold as thin film battery. But they are all primary batteries. They are not rechargeable batteries. So after a lot of discussion, we arrived at a conclusion that over a project period of 3 years, if the funding agency, that is a defense, DRDO, can get us those batteries, what you are talking, we will revise our plans and give you those capacities. So it was agreed upon, and the project went on for 3 years. They went on trying. We also, as an academic institution, went on trying. Absolutely no response you get. The phone number that you call, that is listed in the internet, it goes to an answering machine and no response comes. If at all you get a response from the manufacturer, you get a questionnaire with about 100 questions. He says, you answer these 100 questions, then we will try to give you a quotation. Those questions you cannot answer, which means that nothing is coming out. So no battery was there. We went on with our this thing. We underwent our first failure. Then phase 2, this is what it is. So when we are reaching this stage, one of the friends from USA has sent me one packet saying that just now I got a packet of thin film batteries. I have not opened the pouch. I put it into another envelope and I am just posting you. You test it. So when I opened the pouch, it has got 10 small chips, like your integrated circuit chips. And there is a big note which says that this pouch contains 10 thin film batteries. Please use these batteries within 48 hours after opening the pack. After 48 hours, if they don't work, you heat the battery to 120 degrees and then it will regain its capacity. Okay, good. So we tested this battery. It was rechargeable battery. It gives you 55 microampere hour per centimeter square area. This is what we have also quoted now. And within less than 2 days, its capacity dropped drastically. So we heated in the oven to 120 degrees and tested. it regained its electrochemical activity, but the capacity was no longer 55 microampere hour. It has reduced. So we analyzed what is the reason for this, then came to a conclusion. The packaging that he has used, though it looks like a microelectronic packaging, it's not the ideal microelectronic packaging. There are two kinds of microelectronic packaging. One is called polymer packaging, the other one is ceramic packaging. Polymer packaging is not 100% foolproof for moisture. If you want to have 100% foolproof moisture, this thing, you have to go for ceramic packaging. But the cost involved in polymer packaging and ceramic packaging is about 10 times. So for the initial prototype samples, he has not used ceramic packaging, he has used polymer packaging. He has mentioned also. And that is the reason why he said after 48 hours they don't work, because moisture goes in. While putting into the pouch and sealing it, he has put it in a nitrogen ambient and sent, so that no damage will be done during transit. So this is the situation. So this is what it is. So this battery that we have developed with all these glow box, etc., precautions, looked better than the commercial battery that is made by the Symbet Electronics. So you test its capacity. It gives you 55. Even after 100 cycles, it is still about 45 microampere hours. And then we tested further the life existed in the battery even after about 2000 cycles, though the capacity has come down to about 30 microampere hour per centimeter square. So which means that you know how to make a battery, but you don't know how to package the battery. So if you do an effective packaging, the battery is going to work. Now, so now your job is not over. You are still getting only about 55 microampere hours and long cycle life. So what are the underlying problems that are involved? One is the manufacturing technology that I have already explained to you, some of the issues, and materials. Now, in typical manufacturing methodology, people use electronic grade materials if you are making a thin film battery, and you use a very complex equipment, and finally you end up with a simple integrated device. So you try to analyze these issues involved. So you are trying to avoid semiconductor grade materials, which are very expensive. So develop your process around inexpensive chemicals. I'll tell you what it is. Then avoid vacuum technology, which slows down your manufacturing process, and initial capital expense is very high. That means you use inexpensive process technologies and develop high throughput process. That means it's better if you can do roll-to-roll deposition, so that in a short time, large quantities could be produced. So the cost will come down, the battery life will increase. So how to do this? How do you increase the capacity? There are three approaches. One is use the nanotechnology, make what is called 3D batteries. I'll give you examples. Or the other one is use a process like inkjet printing, screen printing, and tape casting, for which you have to make inks of the materials that you are using for making these batteries. Or you develop altogether new materials for the electrodes and electrolyte, such that these materials do not react with the ambient environment, so that you don't have to worry too much about your packaging and all that. This is a very difficult task. Okay, at least let's concentrate on these two topics of 3D batteries and inkjet printing. So, as I said, people are working on different kind of materials. So today we are here. People are using lithium oxide, people are using vanadium oxide. This is today. But tomorrow's technology is going to be different. People are going to use lithium iron for 3D metal oxides and all that. Or silicon composites are also being thought of. Today we are using lithium as the anode material. Tomorrow you can use silicon, which is a far better material. So the voltage also could be improved from your lithium cobalt oxide and lithium manganese oxide, which is 4.2 volts, to which gives you similar capacity of 160 microampere hour per. So this is material side. Now one can use flexible graphene based lithium ion batteries, which will be charged very fast, high discharge rates. So they will be more flexible, more surface area. So it means that in a small volume, you will have more capacity. This has proceedings of National Academy of Sciences of USA. Or the 3D thin film technologies where you make nano pillars of the cathode material, the anode. So that means you have nano rods or nano pillars or surrounding which you build a battery. That means you have got several cells in a small volume. So you connect them together and it gives you a higher capacity. And this is the so-called 3D integrated all solid state rechargeable battery using nanotechnology. So this solves several issues, like it increases your E density as compared to the planar thin film batteries. Applicable for both wet and solid state batteries. So technology, it could be made small, it is a safety, and 3D composite or hybrid batteries also could improve the charge discharge rates because of the lower impedance. Or you develop inks, make inkjet processing. So you build each of these layers separately. See, in inkjet printing, what you can do, you design your battery, your anode structure, cathode structure, and everything. Your ink will move and fill only that portion. So you don't need any other mask things, using different kinds of material, and finally coat it with a packaging material, so your battery is ready. So with but the issue here is that how do you make this kind of ink with high density materials? Because there will be a lot of sedimentation that takes place. So you have to homogenize everything and do this. So this is a good research topic for somebody who is interested in material science, developing the inks of battery materials. Now, the entire thin film battery technology or the concept has started with the so-called power on chip. That means you have got a chip, a microelectronic chip, and you wanted to build a power also onto that one. So it becomes power on chip. With thus the thin film battery research started. Now, is it feasible now? Let us see. If you take a 130 nanometer line with the DRAM chip, it consists of about 10 to the power of 7 or 10 to the power of 8 transistors with a clock speed of 1.68 gigahertz and consume 2.84 watts with an operating voltage 1.1 volt. This is old data. The present day DRAM data will be much better than these numbers. Let us see what happens if this number. Now, using the present day thin film battery technology, if you try to power this kind of device, it needs 10 to the power of 5 layers. That means your alternate layers have to be 10 to the power of 5. We struggled hard to have 3 or 5 layers in this battery. So you should be able to develop 10 to the power of 5 layers. Now each transistor consumes about 10 to the power of minus 8 watts. So if you can do 10 layers, 10 to the power of 5 transistors operating at 10 megahertz could be powered, not gigahertz, megahertz. Now, will you buy such a device? No. Who is worried about megahertz today? People are worried about gigahertz and terahertz. So as on today, it's not feasible. But then all the applications do not require this kind of requirements. There are power requirements where a low power is enough. So even with 3 layers, you can make a battery and still it could power a small devices. Now this graph is a well-known graph, the so-called Moore's law, which predicts the growth of the microelectronic industry as the time passes, which has more or less faithfully followed till recent times. Okay. Now, if battery research also progressed like your microelectronic industry research, then what happens? Battery research gains about capacity of 6% every year. But your Moore's law says that the number of transistors on a computer microchip will double every 2 years. So for this, you have got a proof. For the last 50 years, it has followed. Now, if your battery technology also has developed like this, today you would have had a battery which is of the size of a penny. That means a small 1 rupee coin, which could have driven a car. Is it possible now? No. So, where do we use then this kind of batteries that we have talked so far, even in the next generation? Smart cards, the average current required is about 10 to the power of 10 picoamperes. So you could use it with the combination of ATM, debit card, credit cards, portable healthcare files, security card keys. Such things could be used with this kind of current. RFID tags, which has become the norm of the day, which require a current of about 10 microamperes, could be used with this. Some implantable medical devices like hearing aids, aids for epilepsy, and blood pump, they draw current of about 1 to 4 microamperes, and they could be powered using this kind of thin film batteries with the present day technology. Or you can use this for non-volatile memory backup. So clocks and all that, one can use this kind of batteries. So this shows the list of applications that you can use thin film batteries in your daily life. Today, there are a number of manufacturers, but still all of them are, I would say that they are all at a prototype stage where the capacity is not very high. But then over a period of time, we hope things will improve. So there are, most of them are based in USA. So this is the story of thin film batteries that we have. This was funded initially by defense for the first phase. Once we saw the failure, then with the new idea of putting a glow box and all that, we approached the Ministry of Information Technology. They gave generous funding. So with that, the second phase of batteries, a prototype battery, which has got 55 microampere hour per centimeter square per micrometer thick, working for about 2000 cycles with a reduction of about 40% capacity, has been developed. So the entire work was done by several of project staff and 3 PhD students. So thank all of you, and thank you all for listening patiently. So if you have got any questions, I'll be happy to answer.
Thank you, sir. Now
Yeah.
I request participants, you can ask your doubts. If you need any clarification, you can unmute your mic and directly you can ask to our resource person.
Yeah.
Or you can type your question in chat box. We will read on behalf of you.
Are there any new inventions for flexible batteries? Flexible type of batteries, sir?
Well, as I said, people are working. It has not yet come.
Okay, sir.
Because
Thank you, sir. Thank you.
if you want to deposit on a flexible battery,
Yes.
you have to deposit on the polymer sheets,
Okay.
which means that you cannot use a vacuum-based techniques.
Okay.
So you have to develop inkjet printing or screen printing. So if the technology is developed, then it can be used.
Okay, sir. Thank you, sir. Thank you, sir.
Sir, dear participants, please introduce yourself and then ask the questions. Please, it
Yeah,
will
that will
be-
be better.
Yes, yes, yes.
Now I see one question here. One Vivek Pandey has asked, up to how many years the battery can be used? Can the battery replace acid battery used in automobile? I gave the answer while explaining. It is too early to think of. Now people are working on automotive batteries very rigorously. For example, Tesla is working on batteries. Their objective is to bring out an all battery vehicle. But then as on today in the market, you get a hybrid vehicle wherein you got a battery, you got a petrol, and you got fuel cell also. So as on today, there is no battery that could straight away replace a lead acid battery for cars. It's not possible. But it has come to scooter level. If you buy an electronic scooter today, you get lithium-ion batteries fixed in that one. Not thin film form. It's not bulk form only. Because thin film form will not be able to give you ampere hours capacity. So bulk batteries, but smaller in size compared to a lead acid battery, at least 1/4 size. That's what comes all for your electric scooters.
Thank you, sir. I request dear participants, if you are having any question, you please unmute yourself. You can ask directly to our resource person.
Sir, I am Dr. M.A. Supin from PDA College of Engineering, Gulbarga. We have got a new research lab to develop flying cars. So what type of batteries you recommend, sir? Or what type of batteries?
What is the power that you require for your flying vehicle? It all depends on the power that you require.
Power. That is a single driven power flying car we are trying to
That's
design.
fine. But what is the capacity that you require? Number. Is it milliamp hours, ampere hours?
Okay, okay, sir. I have to.
That
ask
decides
my
the
research
battery
scholar.
pack.
Okay, sir. Okay. Thank you.
Thank you,
What is
sir.
the best place to carry out the experiments? If so, can they allow? Now, I do not understand this question, but what I understand is that you want to do research, this kind of research, and where are the facilities available? Am I right?
Yes, sir. Yes, sir.
Dr.
Seems-
Himanshu Shekar.
Yes, sir.
Okay, now in India, there are a couple of laboratories which are working on full battery technology. If you have all the facilities, they are available in Central Electrochemical Research Institute in Karaikudi, basically established to do research on batteries. There are a couple of labs in Indian Institute of Science which work on bulk batteries. So one can approach them and come as a short-term worker and do research. There is no problem.
Okay, sir. Thank you, sir. Thank you, sir.
So if you can contact me separately, I can give you the contact details of this.
Okay, sir. Thank you, sir. Thank you, sir.
Thank you, sir. Sir, one more question in chat box, sir. Shall I read it, sir?
Yeah.
Present automobile sector using lead acid batteries. Is there any of nature eco batteries coming in future? Disposing of batteries problem.
Disposing batteries is always a problem. Even your lithium-ion batteries, this is one of the worries that people have got. Lithium is not a very good material. It's a toxic material. So with a lot of mobile phones that are coming up, and every year or two people changing the mobile phones, throwing the old phones, what is going to happen to these old batteries? It's an environmental issue, and so far there is no solution. What is the scope of sodium batteries instead of lithium? Now, sodium batteries, magnesium batteries, lithium air batteries, people are working still in the laboratory scale. If they come out, the environmental problem could reduce at least a bit, at least with magnesium batteries, if not with the sodium batteries. Now, the other question, what is the necessity of sodium-ion battery in comparison with lithium-ion battery? Very simple. Lithium is toxic and highly reactive. Sodium is also reactive, but it is not that toxic as lithium. And the lithium resources are limited, whereas sodium resources are there.
Okay, sir. Thank you, sir.
Sir,
Yes, sir. Please, sir.
Sir, myself, Rajesh from SVC, sir.
Yeah.
Sir, this is a generalized question, sir. Actually, whenever a battery is working, sir, the cycle will be from 0 to 100. But many people will be saying that whenever if you discharge at 90% and we start charging from 20%. Sir, is it so correct, sir? Can we able to increase the battery life like that, sir?
Now, there are two issues. What if we are talking about lithium-ion batteries in mobile phones? Okay.
Yes, sir. Yes.
Now, most of the other battery chemistries, they have got something called memory effect. Now, if you discharge the battery to say 70% and charge those batteries, next time they will discharge when it comes to 70. That means it has stored in them that at 70% I have to be charged. Whereas lithium-ion chemistry doesn't have that memory effect. So whether you do charge it at 90 or 50, the battery life will not affect. It will be same, don't worry. You will charge it fully.
No, sir. Can we able to increase the life, sir?
Well, that's what they say. See, no battery should be discharged fully, honestly.
Okay,
You don't go to
okay.
zero and start. Okay.
But
So
what
normally,
happens to the cycle, sir? Cycle of the battery? Whether if it is given on 10,000 cycles, if you are not discharging fully and charging fully, whether it may be increased to 15,000 cycles?
yeah, it is because it's a material, no. Whereas if you discharge it fully, go to zero
Sir.
and then start charging, then your life will reduce.
Oh.
So
Okay,
don't
sir.
ever
Thank
go
you,
to
sir.
zero.
Thank you, sir. Thank you, sir.
So try to charge the battery when there is some capacity in that.
Sir, thank you, sir. One more question from in chat box, sir. Sir, free softwares mean for these batteries related. And please mention about the softwares used for these measurements. I'll read it once again, sir.
No.
Free softwares mean for these batteries related. I think he is asking free software, sir. I think. And please mention about the softwares used for these measurements.
See, normally when you buy an equipment for battery testing, you get a built-in software and that you use. That's all. You will not be even allowed to copy it.
Okay. Oh, thank you, sir. Thank you, sir.
Sir,
I
Mohan Rao,
request-
sir.
No.
This is Chandrasekhar Reddy, sir, from SV
Yes,
College
sir.
of Engineering.
Yeah.
One question is a generalized question. How to manufacture recycle-friendly batteries? Is there any method is available, sir? Manufacturing of recycle-friendly batteries.
What do you mean by recycle? That means once the battery is thrown out and again take that and charge it.
Yes, sir. Yes, sir.
Refurbishing.
Recycling.
Yeah, recycling I do not know whether anybody is doing that. I'm not sure.
Okay. Yes, sir. Yes, sir. Is there any method is there to recycle the batteries, sir?
See, when you say battery is dead,
Yes, sir.
that means the materials that you have used inside have lost their electrochemical activity.
Yes, yes, sir. Yes, sir.
So that material has, see, at the most, what you can do, you can use the can, the dabba outside.
Outside the box only.
Yeah.
What
Nothing
about
else
the
could be-
cathode cannot be.
No. See, at the most, anode you may recover, but not the cathode.
Okay. Okay.
See, anode is a metal layer, so that metal could be polished and used it and all that, but not the other materials.
Okay.
Thank you, sir. Dear participants, you please ask your questions.
If anybody doesn't want to ask now, or you can always contact me. I gave my email address gmrao@iisc.ac.in. You can contact me anytime, no issues.
Thank you, sir. Sir, shall we go with the vote of thanks, sir?
Yeah, it's up to you. If
Yes,
there are no
yes.
questions, I think we can go.
It seems, sir. Yes, thank you, sir. Thank you for your wonderful presentation, sir. Your presentation added more value for this short-term training program. Really, it is excellent presentation, sir. You have given good knowledge about the thin film micro batteries for next generation devices, which are useful for all the participants and particularly for the research scholars who are currently doing their research. The takeaway from your presentations are very high. You have started with introduction and history of batteries and batteries of yesterday, today, and tomorrow, working of lithium-ion battery on solid-state lithium-ion electrolytes and thin-film microbattery, realization of thin-film batteries, then typical sputtering system, then electrochemical analysis, electrolyte, lipon deposition, oxynitrate glass, and the effect of humidity on lipon layer, and what all factors lead reduction on ionic connectivity, lipon on titanium silicons as second layer, and third layer in thin film anodes and electrochemical analysis, sputtering of tin, then mask patterns, a different mask, platinum coated vapor, then a sputtering system with the glow box, how to increase the capacity, 3D thin film technologies are the key. 3D batteries by inkjet printing and power on chip. Is it possible now? Finally, you have told applications of thin film batteries. Thank you very much, sir. It is a really excellent presentation, sir. Now I request our convener to conclude this session with thanks for the resource person. Requesting Chandrasekhar, sir.
Sir, good morning, sir. This is Dr. M. Chandrasekhar Reddy, convener of this program. On behalf of management, principal, Department of Mechanical Engineering of SVCE, and participants of STTP, thank you very much for accepting our invitation and delivering an informative and thought-provoking webinar on thin film batteries, power source for next generation devices, material issue, organized by SV College of Engineering, Tirupati, in spite of your busy schedule. Thank you very much, sir. And also, I would like to thank my guru, Dr. V. Vasudeva Rao, sir, who has given your contact, sir. I'm also thankful to my guru, Dr. V. Vasudeva Rao, sir. Thank you very much, sir.
Okay, thank you.
Have a good day, sir.
It was a wonderful this thing.
Sir.
Thank you, sir. Thank you, sir.
I hope I could generate some interest in doing some research in batteries.
Yes, sir. Yes, sir. Sure.
Definitely, sir. Yes, sir. Thank you, sir. Thank you,
Okay, thank you. So
actually, we are, sir, we are receiving overwhelming responses in chat box, sir. Everybody is telling thank you, sir. That feedback.
Okay.
Thank you, sir. Thank you. Thank you, sir. Thank you, sir.
Okay.
So, dear participants, please fill the feedback and assessment form. It will be useful for us. Dear participants, please fill the feedback and the assessment link. It will be useful for us to send to the funding agency.
Dear participants, our today's session ends here, and we will continue afternoon session 1:45 p.m. Afternoon session speaker Professor Ajay Sidpara, Professor from Indian Institute of Technology, Kharagpur. The topic is mechanical micro machining. I request all the participants please join 1:45 p.m. itself so that we can conduct the session exactly at 2 p.m. Thank you all. Dear participants, please fill the feedback link and the assessment link. It will be useful for our administration purpose. Professor Logesh sir, already we have shared the YouTube link, sir. You can get through that YouTube link all the sessions of this fourth phase STTP program, all the live videos.